Good afternoon, everyone. Welcome to our webinar today. This is Carrie Williams. I'm the Director of Marketing for Testoil, and I'll be the hostess today. I'm going to start out with some housekeeping things. First, I want to make sure everyone can hear me. So if you can hear me, would you click on the little hand, raise your hand next to your name on the little toolbar. Thank you, Teresa, Trevor, Victoria, Chris, Bob, okay. Alan, Al, y'all can hear me, that's great. Okay, so the webinar today, we're gonna have everybody muted. That's why I'm having you use the little raise your hand function. We have over 200 people registered for the webinar today, and I'm recording this so I can send it to you later. It's a great learning tool. You can share it with others in your office. And so by keeping everyone mute, it helps just make a really clean, nice recording for you to watch later. I'll send that at the end of the webinar, maybe an hour or two after we're done, along with a survey. If you get a chance, please help me out. Answer the survey questions. There's maybe 10. It just really helps me understand what you're looking for and, you know, just how to do better with these webinars. If you do have questions throughout the class today, use the same toolbar. There's a question section where you can enter a question. And I will ask Matt, who's our speaker, I'll ask him the questions at the end of his presentation. And if for any reason the question is a little too technical, then I'll have him answer you directly via email. So submit your questions throughout. If I can interrupt, I will, and I'll ask him the question real quick, but otherwise, most likely we'll wait to the end. Couple more things. We do have some handouts available. There is our ebook, which is just kind of a quick reference tool on report interpretation. It kind of goes along with the things that Matt will talk about today in the presentation. And then we also have a Sources of Metal PDF document that Matt will talk about later during the presentation. So with that, real quick, I did want to mention, you probably have seen the slides on your screen right now. We do, throughout the year, host public training classes. They are certification classes, but the certification is optional. They cover all of the ICML and STLE organization, their certification. So if you're interested in that, send me an email. They're also on our website, and we also provide on-site training and program audits. If that's something you're interested in, also please contact me, Carrie Williams, and that's kwilliams@testoil.com. Okay, so I'm gonna hand over the controls to Matt, and while I do that, Matt, are you there?
Yes.
Okay, so as I'm switching controls over to Matt, make you the presenter. I'll do a quick intro of Matt. So he is a senior technical analyst senior data analyst, using that, with Testoil. He's been with us for nearly 20 years. I think we're coming up on 19, so close enough to say 20. He has reviewed close to 700,000 analysis reports for us. Matt is a STLE certified lubrication specialist. That's the CLS that you might hear throughout the industry. It's really one of the highest level certifications that an analyst can attain. And he is also a certified ASE Master Automotive Technician. And I know the automotive industry is really in Matt's heart. He really loves talking about cars and all that stuff. So in addition to Matt being an analyst, I love to talk about the other roles that he does for us. So he's involved with our industrial services team, where he goes out and does on-site training. He does audits for our customers. He's part of our sample collection team, helping customers set up all of their equipment with our QR codes so they can, you know, scan the bottles and scan the equipment real quick and get everything swept off to us quickly. But really, Matt is very instrumental in helping our customers get their programs set up correctly, and also assisting them on the way. So I know he loves talking to customers when they email him, kind of trying to help them figure out solutions to their problems. So he's really invaluable to Testoil. So with that, I'll say, Matt, how's the weather up there in Cleveland?
Well, it's a little overcast today and a little chilly, but I guess winter is coming, so we'll be getting snow here pretty soon. But yeah, thanks for joining us. Go ahead, Carrie.
I was just going to say, I'm guessing for some reason my weather down here in Houston is about the same. I don't know. We're in the barely 60 degrees, gray skies. It's been raining for weeks. So anyways, I feel your pain with winter coming. All right, well, go ahead. Thanks, Matt.
All right. So again, my name is Matt McMahon, and I'm been at TestOil for a while, and I've looked at quite a few reports, and today we're going to talk about report interpretation. And, when I take a look at the reports, I kind of ask myself, what is the condition of the lubricant? What is the condition of the machine? Are there any kind of contaminants that are present in the system? And the advice I give a lot of our customers is that, depending on your goals, you may want to be more focused in certain directions than others. For example, if we had a really small sump machine, we might not be as concerned with lubricant condition as far as, trying to get 10, 20 years out of it, but we might be interested in, what's the condition of the machine? Is the machine wearing more than usual? And we would want to bias our test packages accordingly. Suppose we have a system that's 10,000 gallons. We might want to bias our test package selection, whatever test that we're wanting to run, on tests that focus on lubricant condition. If there's potential for a certain contaminant to be in our system, we definitely want to add that particular type of test, whether it's water or particle count or things like that, to our test package. So a lot of times I like to see people, take an active role in selecting the packages, because it really, as far as it goes on my end, the more information that I have regarding what's on the report, the more likely I can come to the correct conclusion on, what do we need to do to move forward, what needs to happen to fix the issue that we're having. Now, the first test that we'll talk about today is viscosity. And I would say probably, I can't imagine there's not very many samples that come in that don't get this test. This is kind of like a very basic test. We're measuring the thickness, or what people say, the resistance to flow of the lubricant itself. Ideally, industrial oils are measured at 40 degrees Celsius, and motor oils are measured at 100 degrees Celsius. And on the report, it's reported as kinematic viscosity and centistubs. So, a lot of times when I'm taking a look at the report, especially when it comes to viscosity, knowing what kind of oil is paramount. And I think you would be surprised at how many samples come in that don't have an oil identified, and that really handcuffs me with regards to, I can't give a recommendation of whether or not this is in or out of range if I don't know what the oil is. Now, if we know what the oil is, and these limits that are on your screen right now are primarily what we use for industrial oils, and that will be my focus today, is mainly industrial oils. So ideally, you want your viscosity to be within 10% of your ISO viscosity grade. And the example that I have on here is, if we have a viscosity grade of 100, we would expect the result to be between 90 and 110. If it's outside of 10%, but not outside of 20%, we would call that a marginal condition. And I get a lot of questions from customers that say, hey, we've got these, we're new to you. We have these different ratings on the reports of marginal, critical, and normal. What is the intention behind those? And my answer to that a lot of times is, marginal is we're kind of letting you know that something's a little bit out of range, but maybe not, not super, it doesn't need to be addressed immediately, but we want to bring it to your attention that, hey, something's a little bit off. But if you get a critical condition on the report, we're saying that, hey, we think you need to be making some type of intervention with this machine. On here, if it's outside of 20%, we're going to rate that report critical. So let's take a look at an actual report. So on this report, I always start from top down. On this one, I've highlighted what the lubricant is. The lubricant is Mobil Gear 634. Now, if we didn't really know what viscosity grade the Mobil Gear 634 is, we could always take a look at our new oil column. And for most of our oils that we have in, we have a pretty good library of oils. Now, we don't have every single one that's on the planet, but the main ones, especially mobile products and Shell and lubrication engineers, we have a lot of different resources when it comes to what the new oil should look like. So this one does have a new oil column populated. If you get a report that doesn't have it populated, that means that we haven't seen a sample of new oil of that product. And we won't, until we get one, we won't be able to populate that column. All right, so we're working top down. We want to know what is viscosity grade of this product. And the new oil falls at 437.9, and that's within 10% of a 460. So a 460 is our viscosity grade for this product. And taking a look at this particular sample, we can see that this has definitely had some viscosity issues. And I like to use this one as an example because I believe that this is a straight viscosity issue. There's a misidentification going on here between what is in our database and what's in the actual machine. So it looks like this sample, when is this from? This is from this December 2009 sample back here is a 423. And that's in the ballpark of a 460. However, we can see that the very next sample went to a 220, and that's like 2 grades away. So of course that's going to be rated critical. It was 220 the next one, 230 the next one, but then our most recent report has 327.3. So we've gotten closer. This is the next grade up from a 220 to a 320, but it's still not the right product for what we're saying that's either on the report or in our database. So when I see reports like this, to me, this is an oil identification problem. This isn't necessarily, a problem with the oil itself. This oil probably is supposed to be a 320. It looks like a 320, but we're saying that this machine should be having a 460. I see this happen a lot with new programs. Usually, the first time that we see samples from a new customer, and we get the information from their database, we put it into our system, and then we do the first round of samples. I would say that this happens quite often. We'll run the first set of samples, and a number of them will be flagged for viscosity, and when you look at it, it's really an issue of identification, not necessarily that, oh, this oil is bad, it needs to be changed out. Well, if we change it out with a mismatched lubricant, we're not really making any progress. But on this one, I would recommend we need to take a look at, hey, what's really on the machine? What are the guys putting in this thing? And do we need to update, let Test Oil know that we're actually using a 320 instead of a 460? But that's where we would go with this particular report. So another common test that we run is called elemental spectroscopy. And if you're familiar with oil analysis reports, this is the section where we list all the different elements, all the metallic elements. And we measured 20 different elements, and they're broken down into general categories of wear metals, contaminants, and additives. On the report, they're in parts per million. And I like to say things like what we have up here on the screen, measures metals in solution, which kind of goes along with solid debris below 7 microns in size. It's blind to larger particles. This is kind of really important when we talk about report interpretation. And also it kind of like dovetails into test package selection. Once you understand that, if we have let's say you have a very large gearbox that when it goes into a failure mode, it generates very large particles, but not very many small particles to go along with it. We wouldn't want to rely on this test alone to find that kind of problem. And so if we understand that this particular instrument has a limitation where it can't see very large particles, we would want to back it up with another test. And we'll talk about some of those other tests in a little bit. But that's a key thing to know about interpreting the data that we're going to get from this particular instrument. Just very briefly, we do have that handout on wear metal sources. I mentioned them here too. If we're taking a look at the report and we see one metal dominant over another, or a mixture of some, like copper or tin or lead, it can point us into certain directions of what exactly is wrong with that particular machine. Now, we may have a machine that doesn't have a big variety of metals in it, and that would give us information on, hey, okay, we're seeing a lot of iron. Is this really, it doesn't really matter whether it's metallic from wear or from corrosion. This instrument will report it either way. You know, if it's iron, whether it's iron oxide or some type of alloy, it's going to come back with iron. So here we have some common ones: iron, copper, lead, and tin. Some other wear metal sources are aluminum, chromium, nickel, and silver. And let's take a look at a report with a wear issue.
Matt, can I jump in real quick? Will you take a just explain the new oil column? I do have someone asking me if that's filtered or unfiltered oil, and maybe you could discuss the difference between the reference oil that we used to call that column.
Sure. Yeah, and I can use this report right here that has one. So this one here has our lubricant is Conoco Multipurpose RNO 68. And for this new oil column, you know, what it is at some point, a customer has sent us in a sample of new oil. It's not, you know, whether it's filtered or not, it doesn't really matter, because we're not going to use the particle count as an alarm. You know, we're not going to say that because your sample is dirtier than the new oil, that's not exactly the alarm that we use. And I'll talk about alarms for particle counts in a little bit. But on this, you know, for the new oil column, that's exactly what it is. If somebody has sent us a sample of new oil, we run it in a house account, and then we attach that onto the oil. So when you take a look at the report, you know, that new oil is attached to whatever it says here on the top of the report. You know, it's like I said, this one says Conoco Multipurpose RNO 68. Somebody has sent one of those in, and then we attach it from that point forward. Now, let's say there are some options. Let's say that we have a customer who says, well, you know, I'm very particular about what I want to see on my new oil column, and I only want you to use what I send you. We have provisions that can do that. You know, we can attach new oils from a particular customer to their reports only. But again, we're kind of using the bank of knowledge from everybody to post these. That being said, you know, if there's a big difference between the lab number of the new oil and yours, you know, one being very small and one being very large, you know that perhaps that's an older reference that we might want to get an updated information on. Industrial oils, you know, I've been looking at reports for 19 years. For the most part, industrial oils don't change that much year to year. You know, every now and then we'll get a formulation change, but I would say that a lot of them pretty much stay the same as they've been the last 10, 15, 20 years. That's industrial oils. If we're talking engine oils, there has been a lot of change in formulations with those over the years. So it really depends on the product. All right, so this particular report, what we're taking a look at is wear metals. And on this particular one, I have highlighted the significant number for tin. So we had an issue on this June sample, and we have on the June 21st sample, we have 722 was alarmed critical back then. It appears that this was run, and we actually have a note here from the customer that says that this is a post-failure sample. So they received the critical, they kept it running, the machine had further issues, and now we have it. And it's good for us to talk about, because this is what it's gonna, you know, these are things that we can catch earlier on before it gets to this point. But it's a good example for us to talk about today, because it shows you, hey, this stuff shows up. You know, this isn't like voodoo that we're doing. This is hard science, and we have a significant tin number. Now, whenever we get a high wear metal, we'll add another test called analytical microscopy or analytical porography. And just kind of like as a side note, notice the particle count on this is significant. In fact, if you get a report with all 9s on it for particle count, that essentially means that it's so dirty that it doesn't even run on the particle counter. And this other result before is actually the maximum reading of the particle count. So a lot of particles in the oil. We've got significant amounts of wear metal, especially tin, on this particular machine. And if we take a look at microscopy pictures, we can see some very large wear particles. And when we take a look at these and these pictures, a lot of times I refer back to these when I'm trying to decide, hey, what do I want to make my overall machine condition on this report? We always leave it up to our analysts to have the last word on, how should we flag this report? When I'm taking a look at the reports, especially when I see, one, we have a significant tin number, two, these particles are very sizable. So I know that there's a major problem with this particular machine. So I'm going to make this report critical. But sometimes, and we'll talk about it a little bit more, sometimes you may be above the limit on like iron, but when we take a look at the analytical microscopy, we might find a different story. We might say, oh, well, this isn't really metallic wear or active wear, it's corrosion. And that might change on how I interpret the report, what kind of rating I'm going to give it. But we give a lot of leeway to our analysts as far as what's the overall machine condition. Just because we have this high number here, we want to take a look at that additional information from the analytical microscopy to make a decision on, is this marginal, is this critical? Maybe depending on the rest of the data that's on the report, it's just we can see that perhaps it wasn't the best sample. Maybe it's not a representative sample. And, that can happen where, let's say we have an unusual particle count and we see a lot of dust and debris. We're going to see some other stuff too if we haven't pulled a really good sample. All right, so in general, I can give you a number on wear metals. I can say, hey, your iron's 50. Okay, is that good or bad? We have to put limits on these numbers. And, for my example of iron of 50, let's say that we have a small gearbox. 50 might be perfectly normal. But if I said, hey, you've got an iron 50 on your turbine with 1,000 gallons of oil, that's a lot of material. So depending on the size of the machine, the type of machine, that's where we want to take a look at and decide what are our limits. Is this a normal number? Is this 50 okay? Is this 50 not okay? That being said, as you can see on the screen, we say limits should be based on trends. So a lot of times when you take a look at the report, especially if we have historical data, when we have a lot of information from that particular machine, we could say, yes, a 50 is unusual because previously it's been steady at 10 parts per million. Or we can say 50 is not a problem because it's always been 50 the last few times that we've seen it, or we have a slowly increasing trend that we're seeing. That being said, operational conditions can affect wear metal levels, meaning, if there's an oil change or it's a brand new machine, or we've changed the way this machine runs or the type of load that it's under, can make a difference. And I think that, especially with loading or changes in that, sometimes we don't, as analysts, we don't get that information. And so we may see, oh my gosh, this iron has increased quite a bit. You receive the report back and say, we're changing what we're doing with this machine, and that is the reason why we're having that particular issue. All right, so the other category of elements are contaminants, things like silicon, boron, potassium, and sodium. Let's take a look at a report that has a contamination issue. So again, working top down, we have machine type. It's a hydraulic system. It's using an anti-wear oil with a viscosity grade of 46. And right off the bat, even before I go down and look at the rest of this report, I'm already thinking, all right, anti-wear. I should be seeing elements like phosphorus and zinc. That's part of the anti-wear package. Some of them have calcium in them as well. So let's take a look at what we actually have on here. All right, so we do have those additives that are common to anti-wear. We have calcium at 50, phosphorus at 382, zinc at 450, and we have a pretty good correlation between our current result and the new oil. And again, I always just kind of, if those don't match exactly, I'm not too bent out of shape with regards to, oh my gosh, this phosphorus was 334, I've got a 382 here. as long as it's in the same family of lubricants, like this being an anti-wear, I'm usually not going to call that out on a report. All right, but what we don't have in the new oil that we have in our current sample is silicon at 68. Typically, our alarm limits for silicon on most oils is we don't like to see anything above 50 parts per million. So we're going to alarm this one, and sometimes we can take a look at the particle count data. A very common question I get is, I've gotten a report with a really high particle count, but I don't see anything on the elemental thing. I don't see wear metals. I don't see contaminant metals. How can you have one without the other? And the example that I give a lot of times is, suppose I was, we had a machine and we were taking samples of the machine, and I walked by and a rag fell into the machine. A rag falls in the machine, it gets shredded, and it gets, it passes through the machine, and if we would pull a sample, we would end up with a really high particle count, but we wouldn't necessarily see anything along the lines of metals. A rag doesn't have any additives on it. It doesn't have any contaminants. It's not going to have any wear metals. So again, looking at the report as a whole, we can kind of figure out, okay, what exactly is it here? We can kind of take educated guesses on what's happening. This one here, I just happen to know that the reason why, and this is kind of unusual, because you would think that a machine with like let's say a bad breather or a hatch that was left open or anything like that, where we're just over time getting dust and dirt into it, we would see a gradual increase in silicon, but we're not seeing that with this report. We just see, before it was undetected, and now we see a 68. And I know from this particular report that where this really came from was this particular customer is using reclaimed oil, and their reclaimed oil had a significant amount of silicon in it, and then of course they topped off or they swapped it out. Notice there is a difference between the calcium level between the previous and this one. So this is definitely a different batch of oil between these two samples here. And so it was swapped out, and the new oil had this silicon contamination in it. It all comes down to what we see on the report itself. This one, pretty much shows a big difference between these two samples. Well, it's different because it's a different oil. All right. So we talked a little bit about additives already, and some of these are magnesium, barium, calcium, zinc, phosphorus, molybdenum. Let's take a look at a report that might have an additive problem. All right, so we've got another hydraulic system, and the lubricant is a product called Quaker Quintalubric 888-68. So if we didn't know anything about it, again, we can kind of take a look at the new oil column and see if it's populated, and it is. So if we take a look at the new oil column, we notice that this new oil actually has tin in it. So this tin it's actually, with this particular product, it's a byproduct of how it's made. It's not, this 268 tin isn't a wear metal. So I like to use this report because it shows you, one, just because we group these into general categories doesn't necessarily always mean that, oh my gosh, it's tin, it has to be a wear metal. Well, not necessarily, not in this case, for sure. What else do we have? Well, it has 80 ppm phosphorus in the new oil. Well, what about our current sample? All right, so our current sample doesn't have any tin. And it has a significant level of calcium, phosphorus, and zinc. This looks a lot like the report we just looked at with the anti-wear. And we know that an anti-wear product can be used in hydraulic systems. But it definitely is, we have a significant difference here between what's in the machine and what we're saying is in the machine. If we take a look at the previous sample, that previous sample did have tin in it. So it looks like this was the correct product back here in July, but now here in September, it's not. All right, so let's keep going down the report and see if we have any other information. All right, so viscosity. The new oil is supposed to be a viscosity grade 68. We have a 46. It was a 68 before. And then also take a look at the acid number. So the acid number of the new oil was 1.31. this product that's currently in the machine is 0.42. It's lower and significantly lower than our new oil. That that doesn't naturally happen. You know, we know that acid number is an indicator of typically used as an indicator of oxidation processes, and the fact that our acid number is lower tells us, kind of tips us off. Wait a minute, this is a different product, and that's what we have going on here. We have a different product. This is a lot like that previous report that we just took a look at with the anti-wear, and the new oil is not that type of formulation. And in fact, this product, the Quinta Lubric, is what we call, it's in the family of fire-resistant hydraulic fluids. So this one here is near systems with open flames, and they want to have a product that's fire-resistant. This product that's in the machine now is not. This is a safety issue. So this would be definitely a critical report. You have the wrong product in this machine right now. And as we talk about, fire resistance, and just notice that the flash point that was previously tested on this as well, that's a pretty high temperature, 276 degrees Celsius. So again, that kind of reiterates the fact that this is a fire-resistant hydraulic fluid that's supposed to be in here, and what we have is not. So again, we detected that first by taking a look at the additives, and that there was a significant difference between the new oil column and our current result and previous results. Okay, so that was talking about elemental spectroscopy. Now we're going to talk about a contaminant, which is water, and the test that we use for that is called Carl Fisher water titration. And it's governed by an ASTM method, D6304. On the reports, you'll find that we may be reporting in percent, that's our default unit, or if the customer has asked for it, we'll report as parts per million. So, when I take a look at these and I see a report with high amounts of water, I always try to keep in mind, well, where is it? Where is this coming from? Is this a condensation issue? Is it coming from the outside? Or do we have a particular machine where we might have internal leaks that are allowing water to get into our lube oil? So here we have a air compressor using a product called Solaris Solube. And if we take a look at this particular one, we can notice that in our new oil column, the way this is formulated is it uses barium as the additive. That's kind of unusual. It's one of the reasons why I like to talk about this particular report, is just to let you see, hey, there are different types of additive formulations that are out there. This particular one uses barium. On our current result, we don't have any, but we don't really see any kind of elements in our current result. In the past, we had barium. And if we keep paging down, we can see some other stuff. And we notice that on the IR that we'll talk about in a little bit, it does have an oxidation number of 146 brand new, which is kind of unusual. Some of the previous reports we looked at, the oxidation was not that high. All right, so we have a particle count issue. Our viscosity is too high. Our acid number is elevated, and here's our water at 0.8416%. So we've got a water issue with this. Our oil is degrading, right? Because one of the things that we look for degraded oil is not only an increase in viscosity, which this was pretty steady. We've had what, 39, 39, 41, 42. Now we have this 47, significant increase. We also see the same thing with acid number. On this particular product, we do have guidance from the lube manufacturer, and they say that we should not have an acid number greater than 1.0 for this product. And this one is above that with 1.65, and therefore it's being alarmed. But, a lot of times what I find with not only this product, but a lot of different oils, that when we tend to have a significant amount of water, it's not unusual to see a corresponding increase with acid number. And in this case, it's a fluid degradation, but in some cases, when we have both of those, both a significant amount of water and a high acid number, it's usually the water that's causing that initial problem. This one here with the compressor, there could be many reasons why we're getting water in this system. It could be an internal leak. It could just be the fact that we're drawing in very humid air, and we're not able to, it's dissolving into the oil instead of going out the airstream. So this one's kind of interesting. It shows a little bit different formulation than we've seen. Let's take a look at another report with a water issue. All right, so this one is what's called a Morgoil system. And these Morgoil systems are expected to get significant amounts of water in them. It's just these things exist in steel mills, and they're in environments with a lot of water in close proximity. So they are expected to get some type of water contamination. In fact, the alarm limit for water on these systems is 2%. That sounds probably very high to you, but if it's less than 2%, they consider that normal on this type of system. All right, so we've got this Morlina SD680 in this Morgoil system, and it doesn't really have much in the way of elemental content. Nothing that I would say that stands out as far as additives. And as we go down the report, I want you to take a look at the relationship between the amount of water and our viscosity on this one. This is one of the reasons why I use this particular report. Notice way back here that this particular load of oil with this 9,999 viscosity, again, that tells you that this fluid was so thick that it didn't even flow through our viscometer. There was an issue. But then this next sample, we have 20% water, 1,222. Remember, our new oil is supposed to be in the 680 range, and we have 700 here. So we have 20%, it's at 1,000. We have 5.96, it's at 1,053. 9.76, 959. 12% water, 1,071. I like this report because it shows that we have some oils that separate fairly easy from water, and we wouldn't really expect the viscosity to be affected. But if we take a look at this other test called demulsibility, I don't want to talk too much about it, but just take it from me that this result here of 0.872, it essentially is telling us that this oil does not separate from water. If you get water into this oil, it's not going to settle out. It's going to stay mixed with the oil itself. And in this case, it's driving this higher viscosity. We have this really high water, and we expect it in this product to drop out. It's not. It's staying emulsified in the oil in the system. When it's emulsified, it's actually giving us this higher viscosity. All right, so we get this report. What is our action? Well, the action on this particular report is that, one, we need to control our water, but probably we're having a hard time controlling the water because it doesn't drop out. So it doesn't drop out because there's something wrong with this lubricant. This lubricant needs to be changed out. It no longer separates from water, which is a key, a key performance issue of this particular product. We have to be able to separate out. It's not, and that's why we have. This is going to be another critical report. Another common test that we run is IR spectroscopy, and where I like to say that where we talked about elemental spectroscopy before, where we were measuring different levels of elements, IR measures different compounds that are found in the oil itself. And some of these compounds can be oil degradation products, they could be contamination products, or a lot of times what I use the IR information for when I'm interpreting the report is, hey, does this match up with our new oil? If we have a significant difference between our new oil and our current sample, perhaps we've got an identification issue with the oil itself, like what we had with that report that we talked about earlier, the one that was supposed to be a 460 and it was really a 320. Maybe we have a totally different product. All right, so let's take a look at a report with the IR issue. So this is a pulverizer. This is a coal pulverizer in a power plant, and it's in a real dirty environment, and it's using this product called ML686. Again, we may not know what exactly that means, we might want to take a look at our new oil column. And in the new, I'm just going to page down real quick and take a look at the new oil. So it doesn't have much in the way of additives, and it's the new oil measured to be 429.9, so it should be a 460. All right, with that in mind, let's take a look at our current sample. We have some iron, but the iron's been, pretty steady. So we don't really have a wear issue here at this point in time. However, as we come down to the bottom end of the report, notice that our new oil column, our oxidation, should be 1 or very low, and yet our samples have been significantly higher than that. The latest one being 103. So our oxidation being high can mean one of two things. One is a contamination with another product, one containing ester, or it's indeed a degradation issue. So with the degradation issue, other things that I would like to see are, do we have increases in acid number? Do we have increases in viscosity? And as we take a look at those results, sure enough, here we had a 628, a 686, 715, 724, this increasing trend of viscosity. And then that's coupled with these numbers that we have for the acid number, 0.56, 2.4, that right there is a significant jump. I get a lot of questions from customers asking about, hey, my acid number increased from this number to this number. Is it significant? Sometimes it's not. There's a little bit of leeway in a lot of these tests where we might not get to the second decimal point, the same result. But this is definitely a significant increase, and it continues. 2.4, 5.3, 13.8, 14.25. All right, so this is all telling us the same story. And the story is that this is an oil degradation issue. At this point, we definitely want to change out this oil, and it's paramount. Since this oil has been let go this long, it's going to be really important to flush this system out. If we left any significant amount of oil, this particular fill of oil, in the machine when we change out the lubricant, our new lubricant is going to come under attack almost immediately from these acid products, and we're not going to get full oil life out of that next fill. All right, so acid number, we talked a little bit about that so far, and generally it's governed by a method 974, and we have here, it says indicator of oil serviceability. What does that mean? What it means is that when we have increases in acid number, we have to look out why. And the two reasons I can think of off the top of my head why we might have an increase in acid number is, one, the very reason the very report that we just saw with a degradation issue, or somehow we are getting another product in there that may have a higher starting acid number. So our rules of thumb with acid number is that it's lowest when the oil is new and increases with use. And I just had a question. In fact, I find it interesting. I just had a question about this next point this past week. Acid number of a used oil is typically compared to original acid number. The customer had emailed in and was asking, hey, what are your guidelines for acid number? Because you alarmed my report, and when I talked to the manufacturer, they don't have, or when I look at the product data sheet, there's no guidance as far as acid number goes. And my reply to that was, well, acid number, especially starting acid numbers, really depend on how much additive is in there or the formulation of the oil. So I just can't tell you, hey, if you have an acid number above 0.2, you need to change the oil. That doesn't really apply for a lot of different products. So let's take a look at a couple of samples with issues like this. All right, so we've got a compressor using this product called Clear Lube RS32. And if we page down and just kind of take a look at the new oil column, it doesn't really have much of an additive package as far as metals go. Our oxidation is 3 on the new oil, and let's kind of take a look at here. So it's a viscosity grade 32, but we don't have any information on the acid number of the new product. So that's not that, that's not. I would expect this kind of product. It's a mineral oil because it's got this really low oxidation. It's 32. I would expect this to have a fairly low starting acid number, mainly also because it doesn't have anything in the way of additives. So it's probably going to be very low. All right, let's take a look at the report. I think the key part of this report is notice that these two sample dates are very close to each other. So we have here at October 13th, and then we have one October 22nd. And so what happened? So we had this sample. It was getting reports done on it, and here we sent out a report with a 67 oxidation and a 45.7 with a 5.0 acid number. It looks kind of like that other report, doesn't it? Where we have a degradation issue. So we have the big three here: oxidation is high, viscosity is increased, and a significant jump in acid number. Now, the reason I like to talk about this report is, remember how I just mentioned about changing out the oil? Well, they just did a simple drain and fill with this system, and notice this is brand new oil on this sample, and we're already at a 2.5. And look at the history. 0.39, 0.44, 0.50, the significant increase. This is way higher than what we've seen previously on that fill of oil. So already we know that this oil is under attack. And look at the oxidation. Our new oil is supposed to be 3. We already have a 22 with this brand new oil. So this is a case where we didn't get all of that old oil out, and now our new oil is under attack by this oil that's gone bad. Let's take a look at this one. This report is, you've heard me talk about how additive levels affect acid number, especially the starting acid number. Here's a report for a new oil. And this oil, this product is called Castrol Optigear A320. This oil is primarily used for wind turbine gearboxes. And wind turbine gearboxes have kind of a challenging environment. They're under a pretty good load. There's not a lot of sump. They can't have thousands of gallons sitting on top of these things. So the sump sizes for the given load are typically kind of small, and this is a challenging lubrication environment. So with that in mind, take a look at the additive levels on this product. So here we have older new oil in the new oil column, and then our current one. And notice that there's big numbers for magnesium, phosphorus, zinc, molybdenum. Those are all additives. And as a result of these high levels of additives, take a look at what our acid number is at. And this is brand new oil. So 3.10 is brand new oil. So, that's why I can't give you some magic number of, hey, if your acid number is over blank, that you need to change it out. It really depends on the particular type of oil that you're using. Some oils, like turbine oils, are going to have very low starting acid numbers. Some oils like this one are going to have very high ones. Another one that comes to mind with a fairly high, significant starting acid number are like engine oils. Engine oils have a lot of additives in them, and it is reflected in the starting acid number. So I always like, I think that's a good one to talk about. I like having that particular report. We mentioned particle count before. In general, it determines the cleanliness of the sample. And what we like to use at Test Oil is a technology called pore blockage. But there are some other types of particle counters out there that use a different technology. You might hear them being called things like optical particle counts or laser particle counts. And that's a different technology. And talking about the differences in those is kind of beyond the scope of what we want to go over today. But I would say that the way I've come to think about particle counts is that it's a ratio of the amount of particles that are entering the oil versus the amount of particles that we're able to pull out. I've come to over the years, I've come to think about particle counts in that fashion. And I get a lot of phone calls from customers, and they'll say, hey, I just got this report back that's got a high particle count. I'm going to change out the filter. And my response to that a lot of times is, well, keeping in mind that we're measuring the amount of particles getting in and the amount of particles that we're pulling out, if you just change out the filter, you're only working on half of that equilibrium. You're only working on how much we're able to pull out. Perhaps our problem is how many are getting in. So a lot of times, if we're taking a look at how do particles get into machines, it could be things like contaminated new oil, or it's got a breather on it from the 60s, or there's some other way that particles are getting in. And sure, we can change out the filter, but if we're not really doing anything with the amount of particles that are entering the system, we may not really see an improvement with particle count over the long term. I think that's something that you keep in mind. Now, as far as what we're taking a look at the report, on the report, they're broken down into 5 different size ranges. So it gives us a particle distribution size as part of the information that we get from the instrument itself. And you'll notice on this particular screen that we have the raw numbers, and these are, so like if we take a look at this one here, whoops, with the 21,801, that's 21,801 particles greater than 4 microns per milliliter of oil. So that's like the raw number. But we take these raw numbers and we convert them into a cleanliness code. And here's how we do it. So if we take a look at this particular one, our raw numbers were 1,945 particles greater than 4 microns per milliliter. We take that raw number and find the range that it falls into. And this particular one falls into, we're between 1,300 and 2,500. So it gets this first ISO code number of 18. When I take a look at the reports, if I see, a little bit of variance of one ISO code from sample to sample, I don't really consider that a significant change. I consider that kind of the same result. But notice that these numbers double for every time that we go up one number in the ISO code. I think that's a good way to think about it. If I get an ISO code that is an increase of 2, we've quadrupled the amount of particles that are in that oil. So as you can see, we take these raw numbers, 1,945, 826, 88, the 4, 6, and 14 size ranges, and convert those into an ISO code. This one converts to an 18, 17, 14. That's where it comes from. That's what you see at the top of the report. So here we're going to take a look at this report. It's using a product called Mobile SHC 626. It's used what's listed as a plumbing bearing. And notice that in our new oil column, we have phosphorus. So this SHC product line has what's called an EP additive package. And anything with an EP at extreme pressure, we would expect to see some significant levels of phosphorus. That's what this has, and that's what our sample has. So as far as interpretation goes, this looks like a good match. It looks like it's the right product. And as we take a look at the rest of the data, our IR information matches up. We're in the correct grade. We do have a water issue on this Lita sample, and we do have a higher particle count than what we've seen previous, and what we, above the alarm limit than what we want for this type of machine. If we take a look at the analytical microscopy on this one, we see a lot of what's described as dust and dirt, a little bit of wear debris. But when I take a look at this, especially given what we've seen previously on the particle count, it's never been really clean. These are not low numbers by any means. But now we have this water that's showing up. And the one thing that I always kind of consider is, how was this sample taken? Was this sample taken from a drain port? If this is from a drain port and we didn't properly flush, this is what I would see. I would see a elevated particle count, and I would see the presence of water. So I always think of this particular report as perhaps this was not the best sample technique when we pulled the sample. It seems very unusual that we went from not seeing any water to seeing some type of water in this particular lubricant. So, sample technique is a big deal when it comes to, especially these two tests, particle count and water. If there's a problem there, or we're not pulling a representative sample, this is where we're going to see the difference. We're going to see the difference in particle count and water. What are sources of contamination? Well, I like to think of these different categories: built-in contaminants. What does that mean? Well, it could be a residual from construction or assembly. Could be new oil contamination that we've talked about previously. Again, we can have external ingression, breathers, seals, and hatches, or we can have particles that are internally generated. And some of the examples here are wear, oil degradation, or filter deterioration. And notice I included oil degradation. Sometimes, especially with optical particle counting, we can find what we call soft particles or varnish or insoluble. There's many different terms for them. But we may see maybe the source of our particles is from the oil itself degrading, turning into these insolubles and soft particles. I like this picture that's on here. Notice that this was from an audit. And when we lifted the lid to this, notice the rust on the bottom of the lid, but also the pretty much, you can see that the desiccant breather is pretty much wiped out from the water itself. So this particular machine, just from looking at it, definitely has a water. We're getting water in. We've overcome the desiccant. We may want to figure out where the water is coming from, see if we can address that. If there's no direct way of addressing that, hey, we need to inspect these desiccant breathers a little bit more often. So at the very beginning of the webinar, I mentioned that we had kind of the elemental spectrometer has a limit of 7 microns for particle sizes that it can detect, and that it is a good idea not to totally rely on that test when it comes to certain machines and the type of wear that we would expect to happen if there's a problem with the machine. The generation of very large particles over generating any very small particles. And that because we want to cover all the bases, we want a test that can measure ferrous wear or iron no matter what the size is. And this is that test, wear particle concentration. So we take a portion of the sample, put it into the analyzer, and there's no particle size limit with this particular test, and it reports in parts per million. And I would recommend this on very large gearboxes. Perhaps when we're putting our test package together, we're considering, well, what do we want to get out of this? Well, we're going to pull samples from this gearbox. It's not filtered. All right, well, if it's not filtered, if we do a particle count on that type of machine, it's probably always going to come back pretty high. So are we really going to is there any kind of maintenance action that we're going to do from a high particle count on a non-filtered gearbox? Maybe. Depends on the criticality, but a lot of the ones that we see, usually not. There isn't anything that's done, and they just say, well, it's non-filtered, it's splash lubricated, we're not really too concerned about particles. But perhaps we're very concerned with, hey, is this machine wearing more than usual? And this is where we would want to consider adding this test with a machine like that. Do we want advanced warning of where the machine is throwing off very large iron particles? And heavily loaded gearbox probably is the spot that we would want to use that on. All right, so let's take a look at some reports that have some wear issues with the wear particle analysis. All right, so again, we're starting from the top of the report. It's industrial gear. It's using a product called Royal Purple Synergy 320. So I'm thinking that we should have some type of additive to this. This should be an EP of some sort, I would think, or have some type of extreme pressure additive. I would expect our viscosity to be in the range of a 320. And as we take a look at the elemental end of things, notice that our iron is not that bad. We have a 10 and an 8 for iron. That's not very high. And It does have our EP in it. It's got a phosphorus of 149. Our actual sample is 236 and 283. The oxidation starts at 23. We have a 2931. That's in the ballpark. I'm not too concerned about that. Viscosity is right on for a 320. Acid number is a little bit high, but our in-service is a little bit higher as far as the additives go. So there's not a significant difference between these. I'm not too worried about acid number. However, at the very bottom of the report, we see this significant increase in ferrous wear. And this is why, one of the reasons I love this report. So somebody might say, wait a minute here. We've got 328 ferrous wear, but we only have 8 for iron. You know, isn't that a problem? Well, you know, we're in alarm for the ferrous wear. Let's take a look at the analytical ferrography for this particular report. All right, so this is the reason why. You know, when we take a look at the particles that are present in this oil, we notice that they're really big. They're very sizable. And this is a great example of, we can't just rely on the elemental to pick up wear problems. We have to back it up with either a particle count if we're thinking it's going to be non-ferrous, or if it's going to be ferrous wear, we want to run ferrous wear concentration. These particles are gigantic. They're huge. So this report is showing us that we kind of have a strange particle distribution. We've got a lot of large stuff, but nothing really small to go along with it. This is a serious problem. This is definitely a critical report, and it's something that needs to be looked at very quickly, because this is definitely a problem. All right, so we saw a good example of this, where we have a low elemental and a high ferrous wear. Let's take a look at the next report. This next report, again, we have a gearbox, Terestic 220. Now, Terestic products typically don't have much in the way of additives. Let's see if that's the same with this one. Yeah, so this is interesting. So notice our new oil column doesn't really have much in the way of additives, and yet our sample has a significant EP package. So we've got an oil identification issue here. The machine has an EP in it, but we're saying that it doesn't. You know, is there a problem there? I'm not really sure. Could be an issue. But when we take a look at the iron levels, notice that we have a significant jump from our April to our July sample, from 83 to 269. That's unusual. You know, that's a significant change. All right, what else do we have on this report? Okay, so we have an oil issue. Oh, wow, it doesn't really match up here either. With the IR, we should have a very low oxidation, and yet this product has a significant oxidation number, and it's steady. You know, it's not increasing. So it's a steady oxidation. That tells me that this is part of the oil formulation, that this isn't a degradation issue. Remember, if we're thinking degradation, we're thinking high viscosity, high acid number. This package doesn't have an acid number, but it does have viscosity, and our viscosity is steady. So this is a function of the formulation. So with the EP and the high oxidation, this is a synthetic gear oil that's in the system, and not a Terestic product that is in our new oil column. All right, so we have a synthetic EP. We've got a fairly high elemental iron, and now we take a look at the ferrous wear. Well, wait a minute here. 6, 39, 19, 22. Those are kind of steady numbers. All right, so what does that tell us? Well, even before I go to the next page, just think about what we've seen so far. So we've seen the high elemental. We've seen low ferrous wear. We know that the elemental is sensitive to very small particles. All right, let's take a look at the next page. All right, this is exactly what I was thinking we'd see. These are extremely small ferrous particles that are showing up on the analytical ferrography. That's why we get a significant elemental reading, but it doesn't really add up to much for the ferrous wear concentration. So again, you know, depending on our size distribution, we can get a difference between those two tests that both report iron in parts per million, because one has a limitation and one doesn't. So again, we kind of see where we have very small ferrous particles, and you know, is this a function of what we see up here? You know, a lot of these EP products can be corrosive in nature, these are, if we wanted to categorize things, like if somebody asked me, hey, what does it look like when you see corrosive ironware? This is what it looks like. They look very small, and that's probably what's going on. So this could be a function of we've got the wrong product in here. Maybe we need to go to the Tourestic product so we don't generate so much corrosion in the system. But the main point here is I want you to realize that depending on what we see on the elemental can also, in comparison to the ferrous ware, give us an idea of what the particle size distribution is for these ware particles. All right. But one final report for us to take a look at today. So this one is it's a gearbox, and it's using some type of a 220. We take a look at the new oil column. We can say that it's using EP220. Here's our phosphorus. And when we take a look at the report itself, we see these elements that we don't really expect to see for our EP, right? We've got this zinc. So we had here was a low zinc. I'm not too concerned about that 16, but 113, 243, 83. Okay, those are unusual. Those shouldn't be there. And then we take a look at, well, what else is wrong with this report? Well, we've got some type of a weird viscosity issue. All right, so this old report's 187. It's got the zinc of 27. And then our next report has 138, so it's gone down significantly. And going back up here, we see a zinc number of 113. All right, so then we recover, and we've got a 200, we've got a low zinc. Then we go all the way down to 90, and we have the zinc of 243. And then we send to recover again, so we're back at the 154 with a little bit lower zinc. Now notice that the higher the zinc number, the lower our viscosity is on this particular one. Well, what other kind of oil did we look at today that had zinc in it? Well, remember those first few reports we looked at were AW hydraulic oils, and those hydraulic oils are going to be a lot thinner. Guess what? That's exactly what's going on with this particular system. This system has two parts to it. It's got a gearbox section, and it has a hydraulic section. And here, the hydraulic section is leaking into the gearbox section. So what happens is the customer gets a report, gets a critical, says, oh, we've got to take action. Let's go ahead and change that out. Well, this particular machine is very important to production. They can't stop it. It's got to continue to run. So they can't really stop it and make a permanent repair. So what happens is they get a critical report, they do a bleeding feed, they drain, try to drain out as much as they can without affecting the operation of the machine, and then fill it up with fresh lubricant, EP lubricant. But yet we're not fixing the root cause, which is the leaking hydraulic system into the gearbox. So again, with our interpretation, we can kind of understand, hey, we're getting elements that shouldn't be in there coupled with a low viscosity, hence we're getting a hydraulic fluid in here. Now, we still get samples from this machine that this machine didn't make it to an outage, and they were able to fix it, and now we usually just get normal reports out of this machine. So I think it's a good example of, how do we interpret the report? How do we interpret the data? And we just don't want to take, if we just looked at one thing, oh, we've got a contamination issue. Well, this tells us, well, what is it contaminated with? Well, look at the viscosity. It's quite a bit lower. A product that's lower in viscosity and yet contains zinc. It's a hydraulic oil. So we can combine what we see on multiple tests to come up with our conclusions. And that's kind of like the whole trick of interpreting tests. And I hope that that's what you've kind of gotten from today is, hey, I may make it sound easy, but I've looked at a lot of these reports, and you can get good at this too. It's one of those things where when you just look at them and you see different things, and you're gonna have the advantage over me as far as you're gonna be on the ground floor. You're gonna be there with that machine and understand things that I may not know as the analyst just looking at the report. So I always think of this as kind of like a team effort. The customer did talk about that with us and told us what was going on with it, and that's why I'm relating that to you about how this machine was critical to production, We had to keep it running. We couldn't really fix the problem, and that's why we see that kind of information. So I hope that you found today's webinar useful. If you've got questions, you can feel free to email me. And Carrie, did we have any questions from the group today?
Yes, we've had a lot of questions. I've been able to answer some of them, but there are two that I wanted you to address. One is, what do you do when you receive a sample that the lubricant is unknown? So you don't know the type. Maybe, well, obviously they would tell us that it's, say, from a gearbox, but so what do you as an analyst do with something like that?
Yeah, okay, so the problem with unknown is, the top thing that comes to my mind is that I'm unable to alarm viscosity. So if it comes in, it's unknown, and I get a viscosity of 220, hey, it could be a gear oil. You know, if I look at the rest of the description of the machine, sometimes we have very good machine names where it might say such and such gearbox. And I'll be like, okay, well, that's, you know, that's reasonable to see in that kind of system. But I can't really take any concrete moves as far as, oh my gosh, this is supposed to be a 460 and you've got a 220. So essentially, I can't really give any advice on whether or not the oil is correct because I'm not really sure what's supposed to be in it.
So as far as the gearbox goes, and you know, we have a large customer that's attending this webinar right now. They are only sending in gearbox oils, and for the most part, they don't know what lubricant is in there because they're providing a service to their customer. So what do you do with that, knowing that you know the type of equipment, you know it's a gearbox? Are you still able to provide a level of analysis that's helpful to them?
Yeah, I think what my recommendation would be that even if we don't know this precise product, most likely there's some type of a machine manufacturer recommendation on what it's supposed to be. So, like, you know, your example was a 220. So, you know, it could be Omala 220, it could be a Regal 220, but we don't really know. But we know that it's supposed to be a 220. We do have generic lubricants that we can list on the machine, just saying unknown 220. And even with that additional information, at least I can tell them whether or not they're in grade. Now, let's say that we have absolutely no idea of what's in the machine, or the recommendation is, you know, I would ask people on the ground, hey, you know, what's the word on the street as far as what we put into this machine, and try to get information that way. And if nobody even knows, which is I would find unusual, you know, usually somebody knows what they're adding to a machine. Even if we don't have that information, we can, you know, if we have information on the machine, we can say, oh, gee whiz, you know, it's kind of odd that this gearbox has got a hydraulic oil in it, or it's kind of unusual to see engine oil in this kind of application. So the more information we have, the better. If we don't have enough information, we can make very general statements. But I find that a lot of times when I go and visit plants that, you know, somebody either knows about it or somebody knows what's supposed, you know, the type of oil that's supposed to be in it as far as a grade goes. It's unusual for me if I walk into a place and they're like, yeah, we don't know. You know, somebody knows. Somebody knows what type of product that's being added in there, and at least we can either list it as a generic lube, you know, just an unknown 220, or we can take a look at the type of machine for that.
Here's another question. How do you set particle count limits on machines? Most manufacturers don't give them away. What would you recommend for gearboxes?
Right. So on the top of the reports, and let me, I can kind of page back and I can kind of show you what I'm talking about. So on the top of the report, we have what we call a machine type. This particular report says industrial gear. That's what we use for setting default alarms. Like, let's say we have a customer that has not given us information on, hey, I want to alarm my machine at 15, 14, 10, or 16, 14, 12, or something like that. They're just like, hey, here's our sample. Then we ask for information regarding machine type. We understand that, you know, particle count limits are going to be based on the type of machine. We would expect the turbine to have a lower particle count limit than a gearbox. So for gearboxes, our default alarm limit is 24, 22, 20. It's kind of high, but with gearboxes, we don't really expect them to run as clean as hydraulic systems or turbines or different types of equipment such as that. But I would say, since we're on the topic, I would say that in general, our default alarms for the type of machine, whether it's hydraulic or turbine or gasoline engine or gearbox, that they tend to be on the loose side. You know, they're not really that strict. So we do that on purpose. You know, if we have a new program starting up, you know, along with flagging machines for incorrect lubes, the other thing is we tend to find a lot with high particle counts. And if we made our particle count limits really strict, we would be flagging everything. You know, everything would be flagged, and I think that's not a good situation. I think if I've seen some customers come in with saying, hey, we want things to be alarmed at 15, 14, 10, that's pretty strict. And I think they're overwhelmed when I send them back all their reports with, you know, marginal lubricant conditions. You know, to me, the better way around it is let's start loose, and we're going to definitely alarm ones that need immediate attention. So we go through a round of reports, we flag those, and we address them. And then we, you know, the second set of samples and the third set of samples, hey, things are going pretty good. We caught those really high ones. That's when we start ratcheting down the limit, because we understand that having cleaner systems adds to reliability and machine life.
Okay, I have one last question, Matt. When changing oils, how much oil should you use to flush a gearbox before completing the oil change?
That really goes into, you know, I don't have a precise answer for that. It really depends on the design of the gearbox. If we have something that's splash lubricated and we don't have, you know, we're changing it out by time and not, you know, we're not changing it out because we have a problem, usually a drain and fill is okay. If we have systems with lots of plumbing that we understand that if we stop the machine and just drain out from the reservoir, we may have a significant amount of oil left in that machine, then my recommendation would be to add enough oil in there to run that machine and flush some of those lines and some of that other stuff out, and then drain that and then fill it up again. You know, it really depends on design. You know, I don't have a magic number for, oh yeah, 50% or, oh yeah, 25%. It really depends on the design of the equipment on that one, Carrie.
Okay, I do have another group of questions from a gentleman, but I let him know that you're going to email him later because it turned into several questions in one that you probably better answer than me. So with that, okay. I think I'm going to go ahead and we'll close out the webinar today. Thank you everyone for attending. Watch your email for the link to the recording. I'll also include these handouts as options to download, and the survey. If you get a chance, please respond and answer that survey for me and help me out as I work on our webinar calendar for the next couple months. So everyone have a great day. Thanks, Matt.
Okay.
All right, I'm going to turn this off in just a minute.